Hello. Today's video is going to be about calculating the symbolic formulas for PID gains for a motion controller or motion application. And to make a short story, these are the formulas for the integrator and the proportional gain and the derivative gain. And these are symbolic formulas. The K is the open loop gain. That would have units of inches per second or millimeters per second per volt or per percent output. And alpha is the corner frequency or the bandwidth of the system. What you should notice is that the denominators are the same for each one of these three gains, and that you can take a look at the Ki, and there's a ratio of Ki to Kp. That's basically lambda over 3. And that comes in handy when tuning by feel or just manually. So to start with, what we have to do is import numpy for the math, sympy for the symbolic processing, and IPy is for the, or IPython is for the display on the Jupyter Lab. And I'm using Jupyter Lab, and you can install that by um, doing a pip install Jupyter Lab. So now I'm defining the symbolics, and these are different from variables. Symbols are different from variables, and you got to remember that. So this is the gain, and this is the corner frequency, and these are the three gains for the controller. And lambda is where you want to have the closed loop poles. And in this case, I have three closed loop poles all at the same location so that basically this system is going to be tuned up like a low pass, three pole low pass filter. And I have to define the transfer function for the controller. So I have G sub C, and this is the transfer function, and G sub A, that's my actuator or motor. And the thing is that all you need to do is really change these, and the rest of this is going to work. So another thing that's important to see here is that I can display the formulas as LaTeX, and this pretty prints the formulas. Uh, Now, something I would like to ask the viewers is that for some reason, uh, Python or Jupyter Lab never wants to display the S's in the correct order. I like to display them in order of highest order first. So I would prefer this would be S plus alpha. Um, Yet Jupyter Lab does not do that. So now what we have to do is define the closed loop transfer function. And the closed loop transfer function is this. So you have the controller transfer function times actuator transfer function divided by 1 plus the controller function transfer function times the actuator uh, transfer function. And then I've got to separate that into a numerator and denominator. And if I do that, what I get is this is the closed loop transfer function, this is the numerator, and this is the denominator. And the denominator is important because that is the characteristic equation for the closed loop transfer function, and that's where we need to start with matching poles, replacing the poles. So what we need to do is define a desired closed loop transfer function. And in this case, it's going to be S plus lambda. Lambda is a variable that I can change. And if I increase it, the response is going to be faster. Uh, and then this is to the third order because there's three poles. And I'm doing all this in the S domain. So it's uh, collecting the S's. And then I'm displaying this nicely in LaTeX, and just notice that I got to put a slash in front of the space. Otherwise, it just kind of joins uh, all these words together, and I don't want that. So I like to. Well, I've been a long time user of LaTeX. I use it for magazine articles. It's very good for making printed documents. So now I have the difference of the characteristic equations. So I have the denominator minus my desired closed loop transfer function. And basically what I'm doing is I'm solving for three equations and three unknowns, each with a separate power of s. This is just my shortcut way of doing it. Uh, I'm printing them out. Now this is what the difference looks like. This is the open loop transfer function minus my desired, uh, oh, this is the closed loop transfer function with the controller gains. And this is my desired closed loop transfer function here. And this is without using LaTeX or anything like that. And this doesn't look near as pretty as this. Now, one of the things I would like to know from any viewers is how do I display this so that I can display it so I got descending powers of S. In this case, I got descending powers of lambda, and this seems to work because that's what I have here. You got lambda to the third power, lambda to the second, and lambda to the first. Now, I need to solve for, whoops, I spelled that wrong. I need to spell that solve for the three different powers of S. So I have the integrator, the proportional gain, and the derivative gain, and this will solve symbolically for the powers of S. So basically what you can see is that the denominator is all the same for all three gains. So if the gain, open loop gain, or the corner frequency or bandwidth changes, it's going to change the gains, but it's going to change the gains on all of them, not just one. So now what I'm going to do is I'm going to assign values to the open loop gain, corner frequency, and then to the lambda, which is a parameter that I use to adjust the frequency response. And these are the values. And once I do this, the symbols, if I assign these values to a variable or a symbol, then I've actually changed that symbol from a symbol to a value or variable. So now I'm displaying the integrator gain, proportional gain, and derivative gain here. So now I have the closed loop transfer function, and I have a denominator and a numerator, and I've displayed those using LaTeX. And you can see that this is displaying the S's in powers of S, which is desirable, or at least that's what I want to desire. And then I want to plot out the results of this. So I have these library functions called BodiePlot and PolZeroPlot that I'm importing. And basically these are in my Python path. So they don't necessarily have to be in my directory where I'm doing all this. And in fact, because I'm doing this in Jupyter Lab, it will actually search the Python path to find these modules. So uh, I have cases where the numerator might be 0, or there might be no poles or zeros, excuse me. And then I have the case where I have the denominator and I've got the zeros and the poles, and I'm figuring out their roots, and then I'm doing a display of the Bodie plot and the pole zero plot. And this is the Bodie plot with the closed loop transfer function. And here is the pole zero plot. Now, the reason why this goes over 1, now, and it shouldn't, is that there's zeros in the transfer function, in the closed loop transfer function, and zeros tend to add phase lead. And if you want to remove this bump, what you need to do is either remove the zeros, in other words, put the gains, other than the integrator gain, you need to put the um, derivative gain and the proportional gain in the feedback path only. In other words, they only work on errors. And or you can place the closed loop zeros, and I've got videos on how to do that. So this is the transfer function, and then this is my pole zero plot. Now there's all the poles are here, And then there's 1, 0. You can see this, there's 1, 0 at minus 31. That's actually 10 times 2 pi. And that's here. And this is the 0 that is causing this bump here. So if I place my zeros closer to the closed loop poles and zeros over here, then what would happen is that this would flatten out. And if I move this over here, then what would happen is that I would actually lose bandwidth. You would see this kind of going down like this. So the zeros extend bandwidth, but at the expense of having the possibility for overshoot. And this is why you want to use a target generator whenever you're uh, doing motion control as opposed to doing step jumps, because if I guarantee you, if you do a step change in the set point or target position, you will get an overshoot. So I made this video as kind of a protest against the videos on YouTube, especially the MIT ones where they're writing on a blackboard and you really can't see what's going on. There's no examples. And here you can actually change the gains if you want to. For instance, I can change this gain to 20. That changes the bandwidth. And then what happens is that extends my bandwidth out past 20 hertz. And everything is interactive. The other cool thing about Jupyter Lab is that I'm not copying things from a notes and writing with my back to the audience, uh, to a chalkboard. I think that this is the modern way for instructors to do presentations, and except for my spelling here, and I can change this. This uses markup language, so I can hit escape and change this easily enough. Go, need to change that to an O, and then if I execute that again, it fixes it all up. Another advantage that you have with using Jupyter Lab is that you can export these uh, worksheets or notepads, notebooks as they call them, using, so I can do export, and I can export as HTML, which I like to do because then I can put that on a website, or I can export that as PDF. Another thing I can do is that if I don't force it to display the formulas here, I have the instructions in, or I have the equations in LaTeX. And what's neat about having the equations in LaTeX is if you're writing magazine articles or any kind of document that you wish to publish, you can copy and paste the LaTeX into Microsoft Word. And the advantage that it has is that it will size according to the space that you have. And in my case, I was writing magazine articles so that the editor previously always had to rewrite my formulas and rewrite my plots, but now I'm writing everything in LaTeX, which is sizable, resizable. And also when I do my plots, I have options to output everything in SVG files, which are also scalable. So there's a lot of advantages to using Jupyter Lab for presentations, especially for presentations in colleges. And I really wish that the instructors would use uh, Jupyter Lab more. Anyway, I hope you enjoy this. And if you have any hints about how to display things in the right order, for instance, right here, I would prefer this to be S plus alpha, not alpha plus S. So if you have any hints on how to display that in the right order, let me know. Write in the comments. I am always willing to take suggestions because I want to switch over from my previous Mathcad videos or worksheets over to Jupyter Lab worksheets. So if you like it, give me a like, and goodbye.